So we will see that how is there is a change in terms of its law. So you understand this point that if we increase this mean ionic activity coefficient, then obviously this basically there is a gradient with respect to ionic strength, and also ionic strength depends on the concentration. So if you increase the concentration, basically you are decreasing this what I will say, this mean activity ionic coefficient, right? So as I have said that these ion size parameters, but for a real solution when there is only ion, so you can see that outside some what I will say, some like for an ideal solution is ions are separated and they are very apart from far from each other. So as a result there will be not effect of this other ions. But if you consider a real situation where the concentration is a little bit higher a little bit moderately, then for that case you need to find out this ion size parameter b, and that can be taken that can be find out from extended Debye law. So this Debye law is for ideal solution, right? But for real solution, when there is an interaction of this ion with a different species, so there you have to some parameters had to be taken care of, has to be accounted for. So for that this b is coming, and here you need to find out the estimated value of b in the extended Debye law, right? So like this way you need to approach. So here b is equal to how you will get this b value. So gamma plus minus, that is mean activity coefficient log of that mean activity coefficient equal to minus a z plus z minus root over I by 1 plus b root over I, right? So this is very standard. So if you see these two, here if you see only we are considering log plus minus minus z plus z minus a I to the power half root over I, right? So that is considering that this is like okay, this equation. But here you are getting another extra parameter, that is b, that is ion size parameter, for that is for real solutions. For real, so that I have mentioned that for real solution there is about ionic interactions in between ions, so that's why you have to account it for another parameter. So log of minus a z plus z minus root over I by 1 plus b root over I, and from there b equal to minus 1 by root over I plus a z plus z minus by log gamma plus minus equal to minus 1 by b by b to the power this theta to the power half, because I is b by v0, right? So like this way you have to find out. And this is this KCL, so z plus z minus, obviously both will be 1 and 1, right? B equal to 1.3. Now you have to find out that at equilibrium condition, So here mu equal to mu 0 plus RT ln f by f0. So this f by f0 should be within this log or within this ln value, and from there you can say that, just a minute, yeah, so from there you can say that overall this ln by f0 will be a unitless quantity, right? So it is a standard, and standard what is the fugacity of gas is 1, right? So the free side ideal, the answer will be A. Sorry. So find out the wrong statement here. So activity coefficient is dimensionless, right? Are, are, are you sure activity coefficient is dimensionless, right? In case of an ideal gas, the fugacity is equal to its pressure. Is it? It is absolutely not for ideal gas, right? So this is the wrong statement. The fugacity coefficient is 0 for an ideal gas. That is also correct, right? So statement triple B. So first question we are all have about this ideal solution, Henry's law, Raoult's law, and then we came to that concept called Raoult's law, where there is a mixture of gases and the contribution of each gases we need to figure out in terms of its vapor pressure. So where we need to find out these mole fractions and mole number and mole fractions also, and from there you can do these calculations, and after that we will get to know that partial pressure of one contribution of one of the components in the vapor pressure of each mixture with another gas. So now we have to find out the value. That this is very simple. Just you need to take the root of this, and this now we have to calculate the molar mass of the compound. So this is a very easy and easy way to do it. First you need to find out this called the concept equation, and from that equation you can Raoult's law, basically P by P0. So you from the compared to pure solvent, if there is something mixing is there, obviously the solvent vapor pressure will be decreased because there will be interaction between solvent and solid molecules inside the medium in solution. So this is the mean activity ionic coefficient and activity of a solution. You have to find a millimolar mole solution, molar solution of NaCl, calcium nitrate, NaCl and CaNO3 whole 2. So here is the mean activity coefficient of K7 dilute aqueous solution 25 degrees Celsius are 0.923, 0.902 and 0.816. So state the value of P in the extended D by Huckel law. So find out the value of P, 1.3. So like this we have to also calculate the equilibrium condition mu equal to mu 0 plus RT ln f by f0. Standard fugacity is given, and yes, here the mean activity coefficient of KCl standard dy. So dy equal is for ideal solution, but when this is coming to real solution, there will be ionic and ion interactions. So that plays the prominent role for this. What I will say for this. For the ion. So with this, let me take another situation. So here Raoult's law is for ideal cases, not for a mixture like cases. Find the wrong term. In case of ideal case, fugacity is equal to its space. So that is wrong. Second is the answer. So here you will get this Raoult's law concept. And here also mean ionic activity coefficient, where you will get B value 1.3, and here mean ionic activity coefficient, where you will get this 0.661, and like this way you need to find out some examples.